I'm starting with Unit 5, which is Switching Power Supplies of Power Electronics, B, 6th semester. The reason why we are starting Unit 5 after Unit 3 is that the design of the circuit and understanding of a circuit in Unit 5 is closely related to what we have already studied in Unit 3. The contents of this unit are as listed below. Among these, we will be discussing the introduction and the flyback converter part in this particular lecture. Starting with the introduction of the circuit, what we have already studied in Unit 3 are non-isolated DC to DC converters. All the converters which we have already studied in the previous unit, Unit 3, are non-isolated converters. Why they are known as non-isolated converters? Because in this the supply voltage ground and the load ground were not isolated. They were common. They had a common ground. So if we want to disconnect the ground of the load and the supply, then we need a transformer, and this particular type of a circuit is known as isolated DC to DC converter. It is good to use a transformer. It is in this DC to DC converters, because we have already seen in Unit 3 that they are operated at a very high frequency. The switch is operated at a very high frequency. Okay, so if we design a transformer for a high frequency, usually the transformer size is less bulky, it is smaller in size, so we don't have a problem in a designing. Second is that the circuit design becomes more flexible by introducing a transformer. Why? Because we have another parameter N1 upon N2, which is the turn ratio of primary and secondary, which we can also use in setting the voltage which we require from the circuit. So the level of the voltage is shifted by DC to DC converter, and it is also shifted by using the different values of primary and secondary windings, turn ratios of primary and secondary winding. Also, if we go little further, what we can do is, in a secondary half we can have multiple windings, and using those windings we can have multiple output from the circuit. So we can have multiple DC output voltages by using multiple secondary voltages in case of isolated DC to DC converters. We are talking about transformer so much, so we must know what is the equivalent circuit of a transformer if we want to use it as a part of an electrical circuit. We already are aware of that there is a common core, a magnetic core, on which we have a input part which is known as a primary winding and a output part which is known as a secondary winding, and normal convention of V1 I1 and V2 I2 is as shown in the figure. The relationship between V1 V2 and N1 N2 is directly proportional, that is V1 upon V2 is equals to N1 upon N2, whereas I1 upon I2 is equals to N2 upon N1. If we draw an equivalent circuit for this transformer, it will have a same notation, but there you can see a dot convention also. So basically dot is provided such that the dot at the primary side indicates that it is a positive point of the winding, and dot at the secondary side also indicates the positive point of the winding. The current direction towards the in case of primary, the current is flowing into the dot, whereas at the secondary, the current is leaving the dot. But the transformer has several components. If we model a transformer, it will have R1, L1, R2, L2, which is the equivalent resistance of the primary winding R1, equivalent resistance of secondary winding R2, inductance loss L1, inductance loss L2. There is some useful inductance Lm, which is also known as the mutual inductance, and there is a core is common between the primary and secondary, so there is a core loss which is represented as Rm. In an ideal scenario, we usually ignore all these losses, that is R1, L1, R2, L2, and Rm are ignored, and the useful inductance part, which is the mutual inductance, is usually taken into the consideration. However, in a practical case, these will have some effect in the circuit, but to make the calculation simple and understanding easier, we usually neglect these at this level. So in context to transformer, let us understand, let us just jot down the points which we have just discussed. That is, the dot convention indicates the polarity between the two windings. So when there is a dot, that means the voltage on one side is positive, on the dotted terminal is positive. Okay, but at the primary side, current enters the dot, and while on the secondary side, the current leaves the dot. R1 and R2 represent the resistance of conductors. L1 and L2 are leakage inductance of winding, primary and secondary respectively. Rm represents the magnetic inductance, whereas Rm represents the core loss. So in case of ideal transformer, we will neglect all the losses and we will just take into consideration the Lm value, and we will use a dot convention to represent the direction of voltage and current in our discussion. The first topic of our discussion is flyback converters. Do you remember this circuit? This is a circuit of buck boost converter, which we have already discussed. So what is the expression of output voltage in case of buck boost converter? It is given by minus of Vs into D upon 1 minus D, where Vs is the supply voltage and D is the duty cycle of the switching waveform. Let us see how flyback converter can be designed using buck boost converter. So you remember that buck boost converter design is actually a continuous current mode design only, because the inductor current never reaches to zero. This is the assumption which we have already taken in unit 3. This is the circuit diagram of buck boost converter. Here the switch is being replaced by a power MOSFET, and what other changes we can have is that in place of inductor we can connect a two inductor in parallel with a core in between, and if we disconnect this electrical isolation in between, this is actually a transformer. We also place a dot convention here to indicate the, so that we can find out, we can assume which is the positive terminal of a primary and a secondary winding respectively. What we can do is we can pick this MOSFET on a primary side, C, circuit D, and let us compare first the primary side of the circuit. On a primary side, we have a supply voltage, a power MOSFET, and a inductor in series. So this power MOSFET, since it is these three components are in series, we can pick and place them as desired. So instead of the upper rail, we place the switch in the lower rail. Okay. Now focus on the secondary side. What we have done is we have twisted the secondary side. Instead of the dot on the upper half, we have a dot on the lower half. And what in this case, see, in circuit C, the current through the diode will be such that it is entering the dot point. It is the diode current basically is such that the negative terminal of a diode is connected to this dot. So basically the diode current is entering the dotted point. So if we still want to have a diode on a upper rail, we have to change its direction so that the circuits C and D both are equivalent. So also let us take output voltage convention where positive is the upper half and negative is the lower half. This is how the circuit is. Basically there is a switch, there is a primary winding, there is a common core, and there is a secondary winding where a diode, capacitor and output load is connected. This transformer can be replaced by transformer model as shown, where the dot convention is taken into consideration and the positive polarity is taken where the dot is. Also, we have assumed the direction of current within this transformer as we have discussed earlier. Although the current at the output, the diode, the capacitor and resistor are taken as we had assumed in case of buck boost converter. So there you can find that there's some mismatch in direction of current in the secondary winding. Don't worry about it. This is just a representation where we are using our knowledge base, we are using our understanding to point out the value of the direction of voltages and currents. In case of transformer, we have applied that concept. In case of buck boost converter, we have already seen that this is the direction of current which we had taken into consideration. If in case in a circuit there is a mismatch in direction of current or a polarity of voltage which we have assumed, these will be, if we apply a correct concept, we will get a negative sign which will indicate that your assumption is correct or incorrect accordingly, right? So you can see here, let us see the working of the circuit when the switch is closed. When the switch is closed, during that time, you can note down that the positive terminal of the supply voltage is connected to the positive terminal of the transformers. So here the voltage drop across V1 is equals to Vs. So if this dot on the primary is positive, that means dot here is also positive, which means this is negative. If it is negative, the diode is reverse biased. Reverse biased diode will act as an open circuit. Therefore, current through the secondary winding is zero. If current through secondary is zero, that means the current through primary is also zero. So where is the current flowing in the circuit is only this part of the circuit left, where Vs comes in series with the mutual inductance Lm. So what is V1 equal to? Primary voltage V1 is equal to Vs in this case because they are connected in parallel. So we just note down what we have just derived. When the switch is open, during that time, now the supply voltage is disconnected with the, because it is no longer a part of the circuit, but the current through this inductor will not change instantaneously, so current still flows in this direction. So if the current is flowing through the circuit in this direction, that means that this is negative, which otherwise means this is negative and the upper point is positive. If it is positive, it means the diode is forward biased. So now this, in this case, the energy is being delivered by the current which is flowing through this, and the output current is also flowing through the load as shown. Therefore, the primary voltage can be written in terms of the secondary voltage, which otherwise is equals to V0 into N1 upon N2, because here negative sign is there because we have used the opposite polarity of the dot convention. So what is the drop across the switch? The drop across the switch is all the voltage which is coming in the series of this KVL loop. So we can, in other words, we can write VSW is equals to Vs supply voltage plus V0 into N1 upon N2 using KVL in this branch. Analyzing a circuit for the two conditions, we can find out the critical voltages in the circuit. When the switch is closed, this is the equivalent circuit. We can observe, we have already seen that in this case V1 is equals to Vs. The primary voltage is equals to Vs. What we can write down is V1 is equals to Vs is also equivalent to the drop across inductor Lm, which can be given as Lm into dIlm upon dt. So dIlm upon dt is basically dt equal to delta t, which is the close time of the switch. So during this time, we can write down in terms of duty cycle as d into t is equals to Vs upon Lm from the equation given above, from this equation. So what is this? This is delta I Lm closed, which comes out to be Vs into d into t upon Lm. So since diode is off, I2 is 0, which also means primary current is 0. Current is increasing linearly in the magnetizing inductance Lm. There is no current in the winding, primary winding and the secondary winding of the transformer model. The actual transformer, the current is increasing linearly in the physical primary winding, but there is no current in the secondary winding. In other words, the part of the primary winding is storing energy in this case. In a physical scenario, physically to Lm or primary winding are not different, right? Analysis of the circuit when the switch is open. This is the circuit diagram. We have already found out that the primary winding voltage is equals to minus V0 upon N1 upon N2. So when the switch is open, the current cannot change instantaneously in the inductor LM. So the conduction path must be through the primary turn of the ideal transformer. Now in this case, the diode is also forward bias due to the polarity which has developed across the primary and the secondary winding, and therefore the current flows through the primary winding and induced into the secondary winding, and energy is transferred into the load. So we can write down V1 is equal to primary voltage equal to minus V0 upon N1 upon N2, which is in parallel with Lm, and it can be written as Lm d Lm upon dt, but this is the time when the switch is open, which can be written as 1 minus d into t, and we will equate it and we'll find out I delta I Lm open in this case, which comes out to be minus V0 into 1 minus d into t upon Lm into N1 upon N2. If we do the steady state analysis, we find out that delta ILM closed plus delta ILM open is equal to 0. Substituting the values, this is equal to 0. We calculated to derive the value of output voltage, which comes out to be Vs into d upon 1 minus d into N2 upon N1. Just understand that we have this factor N2 upon N1 extra here. So we were talking about the flexibility of a circuit in this case. So we have extra design parameter, which is the turn ratio of the transformer, which can be selected such that the output voltage is some function of the input voltage. Here negative sign is not there, but because we have twisted the secondary winding, isn't it? हमने क्या किया, हमने उसको पोलैरिटी को रिवर्स कर दिया था सेकेंडरी वाइंडिंग की, इसलिए नेगेटिव साइन यहाँ पे नहीं आएगा. अगर बाकी करंट और वोल्टेज की बात करें तो डायोड करंट क्या होगा, इट इज माइनस ऑफ I1 इंटू N1 अपॉन N2, बिकॉज डायोड की जो पोलैरिटी है करंट फ्लो जो कर रहा है वो नेगेटिव कर रहा है प्राइमरी करंट के, राइट. वी हैव ऑलरेडी फाउंड दैट यूजिंग KVL the voltage drop across the switch is Vs minus V1 primary voltage, which is equal to minus V0 into N1 upon N2. IR is resistor here, so resistor is nothing but V0 upon R. IC is equals to ID minus IR. Okay, so we can write down the value of IC also. IS supply voltage is given by this factor, because here IS is flowing through the inductor LM during the time when the switch is closed, only during that time. So ILM, which part? Only the part when the switch is closed, so into dt upon t. So this is the average value of supply voltage current. We can also draw the waveform for the currents in inductor from the supply voltage, the diode, the capacitor, and the primary voltage here in this case. So all these waveforms I think you can understand, because we already have an understanding of buck boost converter. Just in case you cannot understand any particular waveform, just let me know by sending a message through Google Classroom, or you can send the message to my phone number also. Thank you.